here. And then we can take a look at what we have here. So for this session, all I'm going to be doing is going over the solutions to the practice exam. Starting at the first one, and if you have any questions as we go along, feel free to go ahead and ask away. All right, so the first one says, one of the fastest trains in the world starts from rest, accelerates at a constant rate of 18.6 meters per second squared until it reaches a maximum speed of 289 meters per second. So in part A, we're going to convert the units. We're going to convert the maximum speed of 289 meters per second into miles per hour. And in order to do that, we're going to assume that there are 1,609 meters in each mile. So what you would do is you would go ahead. So this is practice exam. And so we're starting with question 1A. And so we want to convert 289 meters per second into miles per hour. So we have 289 meters per second. And whenever you're doing a unit conversion, of course, all you have to do is multiply by 1. Okay, so we're going to multiply this by 1 mile per 1609 meters. And so this way, what's going to happen is the meters will cancel. So I get miles in the numerator. And then we also have to convert the seconds into hours. So, right, and so this is, this is 1 mile over 1609 meters, right? So that means the same thing as 1, right? We aren't effectively changing anything, right? You don't really change a quantity by multiplying by 1. What we're doing is we're just changing the units that we're expressing the quantity in. So 1 mile over 1609 meters, and then we're going to multiply that by 3,600 seconds, which is the number of seconds per 1 hour. And so what this is going to do, it'll cancel seconds with inverse seconds, and so you're left with miles per hour. And so when you do this math on your calculator, you get 647 miles per hour. Okay, and so that's pretty much how you do that arithmetic, and that would be sufficient to answer the question. You could also write it this way. Okay, that's all. That means the same thing. All right. So let us proceed. And if you have questions, you can go ahead and unmute yourself and ask. And I'll keep going in the meantime. So for part B, we're asked to find the amount of time that elapses before the vehicle reached the maximum speed. Okay, that's what they're asking here. So here, just to remind you, they're saying, part B, find the amount of time that elapsed before the vehicle reached its maximum speed. So how long does it take for the train to get to that final speed of 289 meters per second. So what we're going to do is we are going to use our motion equation. So let's see, let's share that. So if you look at chapter 2 of the textbook, I've got the online version here. You can see there are these very useful equations, equation 2.50 through 2.54. And so these are, you know, some people call them the big five, right? These are the 5 equations that describe one-dimensional kinematics in the sense that you have, when you have constant acceleration, these are the 5 equations that describe the motion of the object, okay, if it's moving in one dimension. So they want us to figure out how much time it takes to go from rest to this final speed. And so, so we would use this one here. Let's see, yeah, because they tell us the acceleration and they tell us the initial and final speeds, and all we have to figure out is the time. So this is the appropriate equation to use. So if we go ahead and do that, we have so the initial, they call it V0 in the textbook. This is your initial speed. It starts from rest, so that's 0. And then your final speed, I think they just call it plain old V in the textbook. So we'll follow the textbook's notation. So this is your final speed. That's going to be 289 meters per second. And then the acceleration is given as well. That's going to be 18.6 meters per second squared. And then the time is what is being asked for. Okay, so we say that V is equal to V0 plus AT. And so this is acceleration. It's in the same direction as the final speed. So we don't need to put any minus signs in here. And so let's plug in what we have, or actually no, first let us solve this for the time, because that's what we're being asked for. So the time, so I'm going to subtract V0 from both sides. Right, so that eliminates it from here, and it shows up as minus V0 over here. Then I'm going to divide both sides by A. And so now we can go ahead and plug in our numbers. So this is going to be 289 meters per second minus 0 meters per second. And we're going to divide by 18.6 meters per second squared. And so you do that, and you end up with 15.5 seconds. Okay, so there you are for part B. Okay, so how's that looking? Looks pretty good so far. All right. If you are following, go ahead and put a thumbs up in your Zoom. Okay. All right, most people are following. Okay, good. All right. Is anyone not happy with what we've seen so far? Okay, if you're not happy with what you've seen, you can go ahead and put a question in the chat. Otherwise, we'll move on. Okay, so let's look at what we have next. So what we have next is known as Part C, and that says find the distance a vehicle travels before reaching the maximum speed. Okay, so for that one, we can go back to our wonderful motion equations. And so we have to find the distance, right? So again, the acceleration, it's still constant, you know, same scenario. And so the only, well, so actually, I guess we do have a little bit of a choice. I mean, we could, you know, since we know the time it takes and we can work out the average speed, you know, we could use something like this. But we don't have to do that. It's probably most straightforward to just use this one here at the end, because here it's got the initial and final speeds squared. It's got the acceleration, and then it's got this quantity, which is the distance that it travels, you know, from start to finish. And, you know, this is what we're going to solve for. So this is a pretty good equation for us to use, 2.54. So let's try that. So here I'm going to go over to the next page. And so this is, we're still on Q1, but this is part C. Okay. So what we're talking about is we're talking about what we have. So if we look at our variables, so the x minus x0 that you saw in the equation, we can also, the shorthand for this is just the change in x, delta x, and this is what we're solving for. Okay, we're solving for this, and the final speed is given, of course, as 289 meters per second, and the initial speed, we're told that it starts from rest, so that means initial speed is 0 meters per second. And the acceleration, we've been given 18.6 meters per second squared. So this is what we're going to solve for. So the equation that has all these quantities in it is that 2.54 that I showed you. So let's go ahead and write that down. So that says v squared is equal to v0 squared plus 2 times the acceleration times delta x. Okay, so I'm using this notation. I'm using the shorthand for x final minus x initial. And so if we go ahead and solve this for delta x, we do a little bit of algebra here. So I'm going to subtract v0 squared from both sides. So I get v squared minus v0 squared is equal to twice a delta x. Now I'm going to divide both sides by twice a. So I have delta x winds up being equal to twice a over v squared minus v0 squared. And so we can plug in, oh, whoops, what have I done? I've done something weird. That's not what I meant to do. Not what I meant to do at all. So let's see, the v, oh man, what am I doing? Okay, so the v squared minus v0, that's up here. Sorry, v0 squared. Now we divide both sides by twice a, so that shows up down there. And so now I can plug in my 0, my 289, et cetera, et cetera. So what I have is I have 289 meters per second, and the whole thing squared here. This guy's just 0, so forget about it. And so down here we have 2 times 18.6 meters per second squared. And we look at our units here. So we have, this guy goes away. This becomes plain old meters. And then we have inverse second squared, that cancels. So this is going to be in meters like we want. And so when we do this out, we end up with 2,245 meters. And that's all we have for that. Okay, so that is question 1 on the practice exam. So hopefully that's pretty comfortable for folks. Although if it's not, that's okay too. You can ask whatever is on your mind. Feel free to ask. It doesn't even have to be about what we just talked about. If you have any question at all, just unmute yourself or put it in the chat and we'll address it. Okay. So that was question 1C. All right, so let's go back to the, let's go back to our exam here. And let's see what we got again for question number 2. So question 2 is about the graduate. Okay. Hopefully some of you are going to be graduating soon. And hopefully we'll actually get to have, you know, a decent ceremony, or although maybe not, you know, because of coronavirus. But anyway, there was a time when like people would gather together and celebrate graduation. And, you know, this is the sort of thing that would happen. You know, a person would throw their hat in the air, you know. Hopefully some of you get to experience this as well. But, you know, I'm not making any promises. So the happy graduate throws their graduation cap in the air, and the cap reaches a maximum height of 1.56 meters above the ground where it was thrown. Then it falls back down. The graduate then catches the cap at the same height from which it was thrown. So question A, find the initial speed of the cap when it was thrown. Okay, and then question B, find the amount of time that passes from when the cap is thrown to when it is caught again at the same height. Okay, so let's take a look. All right, so question 2, part A. Okay, so let's see. So they're asking us for the initial speed of the cap when it was thrown. And so if we sort of take stock of what we know, you know, that'll help inform us as to which of those big 5 equations to use, right? So this is, again, is just, it's plain old one-dimensional kinematics because, you know, the cap just goes straight up and comes straight down. There's no lateral motion to account for. So this is just plain old one-dimensional kinematics. And so, so we know that we're going to be using the equations from the big 5, right, that I showed you in the textbook. So I'm just going to call the y position of the cap, I'm just going to call that x, because you know it's just one dimension, so it doesn't matter. And they tell us that the delta x, this is information we're given, it is 1.56 meters. Okay, so that's the amount of time that the thing, you know, went up into the air. Or sorry, that's the amount of distance that it covered, you know, when it went up into the air. Okay, so, and so the initial speed, this is unknown. We have to solve for this. The final speed, this is going to be 0 meters per second. Why? They didn't tell us this, but how do we know? Because it says that the cap reaches a maximum height. So what happens is the cap, you know, it literally, you know, if I draw this graduation cap, okay, right, so there's the cap, okay, I don't know, I can't really draw something like that. And then, so this thing, you know, goes up, 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 and it stops for a moment, and then it comes back down, okay? So, so there's this moment where it stopped. And the moment where it stops, that's when its speed became 0. And so that height that it reached, right? This is what we're calling the delta x. And so that is the 1.56 meters, okay? So we're saying, okay, what was the initial speed that it had that allowed it to go this far before stopping? And then the acceleration, right, is just going to equal, it's just going to equal minus g. And so that's negative 9.8 meters per second squared, give or take, right? So so it's g because this is happening here on Earth, and we're neglecting air resistance, right? He just flings the cap, it goes up, it comes down, you know, what goes up must come down because of gravity. And so that's what we're dealing with. So now we can go ahead and use equation 2.54 from the textbook. So we have v squared is equal to v initial squared minus 2g delta x, something like that. Okay, so what I did was I used the one that says v squared equals v initial squared plus 2g, a delta x, and I plugged in minus g for a, so that's how come it looks like this now. All right, so now let's see, so what do we do? So if we plug in 0 for v, we have 0 is equal to v0 squared minus 2g delta x. Now we can solve for v0, so that means add this quantity to both sides. So we get v0 squared is equal to 2g delta x. And so now we can take the square root of each side. So we get v0 v0 squared is equal to, oh sorry, hang on, taking the square root of both sides. So we take the square root of each side, we get, right, the square root of something squared is just the thing itself, but here we have 2g delta x. So now we can plug in our numbers here. So this is going to look something like the square root of 2 times 9.8. Yeah, 9.80 meters per second squared. And then we have delta x, which is 1.56 meters. Okay, and so you multiply these numbers and then take the square root of the result. You do that on your calculator, and you're supposed to get 5.53 meters per second, right? Because you see here, I've got meters times meters, that's meters squared per second squared, but then I take the square root of that, so that gives me meters per second. So it all works out, okay? So so that's the happy graduate, the part A. All right, and so you see, it's very important that when you solve these problems or problems like this on the midterm exam, you know, I'm going to be looking very closely to make sure that you're actually accounting for the units, right? You know, if you just put 5.53 and leave out the units, you know, you will only get a very small amount of the actual credit, right? And the reason is because if you're sloppy with units in real life, you know, it could lead to, you know, a train wreck. You know, a literal train accident could happen if you don't report units, or you report the wrong units, you know, to the engineer who's controlling the train, right? I mean, it could cause all sorts of disasters. So I'm trying to train you to, you know, be very diligent about your units, because then hopefully it doesn't lead to, you know, problems later, right? If you're always paying close attention to your units. Okay. All right. So that's part A. So let's take a look at part B. Let's take a look at part B. So part B, just to remind you, it says, find the amount of time that passes from when the cap is thrown to when it is caught at the same height. Okay. So let's look at that. So for part B, so what's happening is the cap, it starts out here, it goes up, and then comes back to where it started from. So that describes a displacement equal to 0 meters. Okay, this displacement, it did not happen. I mean, it you know, it went back to where it started, so that's a 0 displacement. Okay. Oh yeah, and by the way, what I was saying about units, if your answer is 0, I don't really care if you leave the units off. You know, that's, I'm not concerned about units if it's 0, right? Because 0 is just 0. You know, the units don't really matter. But if it's non-zero, then you have to have the units, because, you know, otherwise you don't know, you don't have any context, right, for the quantity that's being expressed. You know, if it is a quantity that normally has units. Okay, so then so the displacement in this case is going to be 0. The initial speed is what we found in part A. So this is what we found in part A. Let me just make a note of that. So this is the answer from part A. Hang on, let's see, this should be the answer from part A. Okay, that's this. All right, and then we got and then we got the acceleration again is equal to negative g, which is negative 9.80 meters per second squared. And then the time we're being asked for, well, you know, how much time does it take? So here we want to use one of our big five equations that has the initial speed in it, has the acceleration, has the delta x, and also has the time, and we're going to solve it for the time. So the equation that has all that looks something like this. Delta x is equal to v initial t plus 1/2 at squared. Okay, and so this may not look exactly familiar, but here we can take a look at our big five list here for a second. So we take a look at it, and you see what they have here. This is equation 2.53. So we've got x equals x0 plus v0t plus 1/2 at squared. And you can see that if you subtract x0 from each side, on the left you're going to end up with x minus x0. And on the right you have v0t plus 1/2 at squared. Okay, so you can see what I've written down is exactly equivalent to this. All right, so this is what we have here. So this of course is the same thing as x minus x0, right? That's the same thing. Okay, and so this is going to equal, it's the same thing as v0t minus 1/2 g t squared. And so the delta x is 0 because it went up and came back to where it started from. So what we're getting at is we've got 0 is equal to v0t minus 1/2 gt squared. Okay. So this is, and we're solving for t. So this, you know, kind of looks like a quadratic, but this is the type of quadratic that you don't really have to use a quadratic formula. You can just factor it. Okay, so we're going to try and factor this guy. So we will factor the t out of each of these terms. So this is just a little bit of algebra we're going to attempt here. So we're factored the t out of this term, so we just have the v0 inside. And then over here we have minus 1/2 gt. Okay, and so it's saying we've got this factor times this factor is equal to 0. So anytime you have something multiply something else equal to 0, it means that either one or the other or both are equal to 0. Okay, so you're going to get two solutions for t that satisfy this equation. Whoops. One of them is t equals 0. If t equals 0, then, you know, this product is going to be 0, and so, you know, t0 satisfies it. But that's just saying that you started out at, you know, a particular place, right? You started out with no displacement, right? That's what that means. And then this other time is going to be some later time, right? So the other solution to this is the one that causes this quantity to be 0, and that's going to be some time other than 0, a later time, which is the time where the hat returns back to where it started from. So this is the solution that we are interested in, because we are interested in what we're interested in the amount of time it takes for the hat to go up and then return, right? So so what we're going to do is we're simply going to set V0 minus 1/2 GT equal to 0, and then we'll solve for t. So I'm going to go ahead and I can go ahead and subtract V0 from each side, so I get minus 1/2 GT is equal to minus V0. Now I can multiply each side by minus 1. And so that's going to make them both positive. So I get 1/2 GT is equal to V0. And then what I'm going to do is I'm going to multiply each side by 2 to get rid of the 1/2 here. And I'm going to divide each side by g to get rid of the g over here. And so that leaves me with t is equal to twice V0 divided by g. And so you can see that if I took this and I plugged it back in here, I'd end up with V0 minus V0, which is 0. And I get 0, right? So that's what we want. That's good. So if we plug in the numbers here, so we'll plug in 5.53 for V0. We plug in 9.8 for G. So here, I'll squeeze this in up here because I kind of ran out of room there. So this says that T is equal to 2 times 5.53 meters per second divided by 9.80 meters per second squared. So the meters cancel. Inverse second cancels with one of the inverse seconds down below. And inverse seconds are just seconds. So this is now going to be in seconds, which is what we want. And so you do this math here on your calculator, and I think you get something like 1.13 seconds. So you throw your hat, up it goes, and it comes back down a little bit more than a second later. All right.
Professor, I have a question.
Yes, go ahead.
With this one and the one before, I chose different equations. Does it matter if we choose something different than you chose, as long as we come out with the same answer?
Yeah, it doesn't matter how you do it. Yeah, if you'd rather use other equations, because yeah, I recognize that you know, there's lots of different ways you can solve these problems. But yeah, however you want to do it is fine.
Thank you.
The main thing is you have to show your work in order to receive full credit, right? And it just needs to be clearly shown.
All right, thank you.
Mm-hmm. Okay, so let us take a look. Well, let's see, how's everybody doing? I'm going through this kind of fast, but okay, looks like I'm seeing some thumbs ups. Okay, good. All right, excellent. Okay, so let's press on. Maybe we can get done a little bit early and, you know, get something cold to drink because it's really hot today. Okay, so let's see. Let's move on to number 3. Okay. So number 3. So here's our marksman. Okay. So the marksman aims horizontally at the center of the target. That is 136 meters away. But when the bullet is fired, it hits the bottom of the target, which is 1.65 centimeters below the center. And they have a nice little picture here so you can see. Okay, so for starters, they want you to figure out the amount of time it takes from when the bullet is fired and when it hits the target. You know, taking into account that it doesn't hit the, you know, the dead on bullseye, but it hits down here. Okay, so so yeah, that's how that works, right? So incidentally, you know, I'm not much of a marksman myself, but you know, I had the chance to go and play some paintball for the first time last year, and yeah, you know, you know, if you ever play paintball and you fire the rifle, you definitely see this happen, right? You know, I definitely noticed that you know, you know, it doesn't fly in a straight line. It definitely, you know, curves down toward the ground because of gravity. Okay, so let's see. So we're going to find the time in part A, time it takes to hit the target, and then for part B, we're going to find what is the initial speed of the bullet as it, you know, as it launches out of the rifle. So let's see what that entails. Okay. Let's see what that entails here. Okay, so this is now question number 3. Okay, so we're looking for the time. So now we're no longer in the one-dimensional kinematics world. Now we're in the two-dimensional kinematics world. Why? Because the motion of the bullet is in 2 dimensions. It goes across over to the target, but it also goes down at the same time. So we have to now consider these 2 components of the motion. So so there's going to be 2 sets of kinematic equations that we're going to be looking at. There's going to be some for the horizontal motion and some for the vertical motion. So if we sort of write down what we know, we'll start out with the with the, let's see, what are we going to do? I guess technically, we don't really need to consider the horizontal motion at all this time. So, okay, let's not bother considering the horizontal. So just know that there's horizontal and vertical. So the horizontal motion I'm going to call X motion, and the vertical I'm going to call Y. And so let's look at just the Y motion for the moment. And so what happens here, I should probably draw a diagram here so that you know exactly what I'm talking about. So for starters, we're going to use a coordinate system that kind of looks like this. Here, let me see if I can draw that better. Okay, we're going to use the coordinate system that looks like this. There's your y-axis, there's your x-axis, and you see y is increasing going up, and x is increasing going to the right. Okay, so positive direction is up, and positive direction is right. So that's one thing. So if we consider the bullet, so here I'll draw. Right, there's the bullet. Okay, and so the bullet is doing something like this. It's going right, and it hits the target over here. So what we're getting at is that this, see if I can do this better. Okay, so the bullet, right, if it had just gone, kept going straight, it would have gone along this dotted line here. And so what we're saying is that along this line, y is equal to 0, okay? And then by the time it reaches the target, right here at the end point here, when it hits the target, this has the y coordinate, y equal to minus 0.165 meters. And why? Because they tell you that it misses the bullseye by 16.5 centimeters. So what I'm saying is that if y equals 0 is up here, so down below that it's a negative y coordinate, right? So that's what's happening with our bullet. Right, here's the bullet, and a bullet is just a projectile. All right, so it goes bang like that. Okay, so our delta y is known as negative 0.165 meters. And our initial speed along y is 0 meters per second. Because initially, as the bullet goes flying out, as it starts out, it has no motion along y. It only has motion along x. But then as the bullet begins to move, gravity takes hold of it, and then gravity begins to, cause it to head downwards. And so over time, it develops motion along y that gets faster and faster, right? Because, gravity accelerates things down toward the ground. Okay, and so what is the y component of the acceleration? Well, that is equal to minus g, and that is equal to minus 9.80 meters per second squared. And so which equation do we use? So we can use one of the big five equations. We want the one, so we're being asked for the time. So here, I'll put that, the time is what? We're being asked for the time. And so So we need the equation that has the delta y, the initial speed along y, and the acceleration along y, and also the time, and we are going to solve for that. So what we have is we have this guy. It looks like this. Delta y is equal to v initial y times t plus 1/2 a t squared. And we can go ahead and plug in minus g for a. We can plug in 0 for v0y. So we have delta y is equal to minus 1/2 g t squared. So now we can go ahead and solve this for the time. So we do that. All I have to do is multiply both sides by 2 and divide both sides by g. And I can also multiply both sides by -1. And so when I do that, I get t squared is equal to minus 2 delta y divided by g. Now I'm going to take the square root of each side. So I get t is equal to the square root of minus 2 delta y over g. And so what does that mean? That means we can plug in our numbers. So here, I'll do that over here. So t is equal to the square root of minus 2 times minus 0.165 meters. Okay, so the minuses cancel each other, so that's good, right? Because you don't want to be taking square roots of negative numbers. If you can help it in this class, so that's good. If you find yourself having to take a square root of a negative number in this class, it means you've done something wrong. Okay. So the meters cancel. So now we have inverse second squared in the denominator, so that becomes second squared in the numerator. But then we're taking the square root of that, so that leaves us with seconds overall. And so that's good because we're looking for a time. And so when you do this math, over here on your calculator, you should be getting 0.184 seconds. So it doesn't take very long for this thing to hit the target. And that's that. Okay, so you don't have to consider the motion along x at all, right? And the reason is because the motion of x and y are completely independent, because those two axes are at right angles to each other. So it means that anything that's happening along here can happen and not affect anything that's happening along here. Okay, so these are independent coordinates. Okay, so that's part A. So I'll let that sink in for a moment. And then we'll take a look at part B. Okay, so for part B, they ask, what is the speed of the bullet as it leaves the rifle? Okay, so let's take a look. So what is the speed of the bullet as it leaves the rifle. So again, what we have is, so now we have to consider the x motion. We have to consider the motion along x. So delta x is given as 136 meters. And the initial speed along x is something that we don't know yet. We have to figure that out. And the final speed along x is also something that we don't know yet. But we do know that the horizontal motion, once that bullet's in motion, the horizontal motion is unaffected by gravity. Gravity only pulls things down, it doesn't pull things sideways. So if it starts out with a certain amount of speed along x, it has to finish with that same amount of speed along x. So this is going to be equal to whatever the speed along x was that you started with. But that's what we're going to solve for. Right? So these two are really the same quantity. They're the same quantity. Okay, and then let's see. So the time, though, we do know. We do know the time because we worked that out in part A. That's 0.184 seconds. So this, again, is your answer from part A. And is there any acceleration along x? No, there's not. It is quite simply 0. Okay, 0 meters per second squared, right? So once that bullet has been launched, it's just going to keep going, or at least it's what do you call it? It's its horizontal component of its motion is going to remain unchanged. Okay, but the vertical component is going to be changing because there's gravity acting on it. So when it comes down to it, we're looking for the speed. So let's see, how do we need an equation that has the initial speed, has the time, you know, and has delta x in it. Sure, it can have acceleration too. It's only 0, so it's gonna drop out. So we can use this one here. Delta x equals v0 x times the time plus 1/2 a t squared. Okay, but if we plug in, oh, sorry, this should say ax, my bad. If we plug in ax equals 0, this whole thing drops out, so we're just left with this. So we can go ahead and solve this for v0x. So v0x, we're going to divide both sides by t. So this is going to be delta x over t. And so this works out to 136 meters divided by 0.184 seconds. And that is known as 741 meters per second. Meters per second. Okay. All right. So there you go. And life goes on. Okay. So I think that was all for problem 3. So now we move on to problem number 4. Question number 4. So let's take a look. Okay, everybody still doing okay? All right, excellent. Okay. Hopefully people are not becoming bored. This is the final of the 4 questions, so we're almost done. All right. So the football player tries to, oh, football, right. Okay, so here when they say football, they really mean soccer or maybe football if you're speaking Spanish. But yeah, that's what they're talking about. So this guy tries to score the goal by kicking the ball into the top of the goal, which is 2.75 meters high. And he kicks the ball so that it has a velocity of 24.8 meters per second at an angle of 51 degrees above the horizontal as it leaves the ground. So in part A, at what point in the ball's travel will the speed of the ball be the slowest during its overall motion? Find the value of the ball's slowest speed during the motion toward the goal. So that's part A. Okay, let's take a look at that, and then we'll handle the others. Okay. All right. So this is question number 4. So the question is, when is the speed the slowest? So remember, the speed is changing of this thing, you know, during the whole time it's going. So if I just draw a quick little diagram here. So we got our soccer ball. Okay. Okay, there's our soccer ball. And so this guy is initially flying with a speed like that has an angle of theta with respect to the horizontal. And so it's going off in this direction. And so this thing, it goes up, 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 up. And then eventually it, you know, it meets up with the top of the goal. And so that's what happens here. And so so it has an initial speed, but and it has, so initially it has both a vertical and a horizontal component to the speed. But then as time goes on, at some point it reaches this maximum position, and at that moment it stops having any motion vertically. It only has the horizontal motion. And then it begins to pick up speed in the vertical direction as it, you know, begins to head downwards into the goal. So the place where the overall speed is the smallest is going to be the time when the vertical component of the speed is 0. So that's going to be somewhere up here, right? So here, we'd say the ball stops rising. and it begins falling. So there's a brief moment in time where it's no longer climbing, and it has momentarily stopped changing its y coordinate, right? The x coordinate, of course, continues, as though nothing happened, right? The horizontal motion just keeps going. Once it's in motion, it's just going to keep going because it's not being acted on by any horizontal forces, right? It's only being acted on by a vertical force, right? Because we're neglecting air resistance. So this is the place where the speed is going to be the slowest. So at the highest point, we'd say at the highest point, Vy is equal to 0. And so V, which is equal to the square root of Vx squared plus Vy squared, is smallest. Right, because this part drops out, this becomes 0, so all you're left with is that, and that's the smallest. Okay, so then with that being the case, we'd say that the V minimum is going to be this value of V where the Vy part is just 0. So that's going to be the square root of Vx squared is just Vx. It's going to be whatever Vx is. And Vx is the same throughout the whole trip. So if you know the initial launch speed, and so this here, we're going to call this V0. It's a vector. And so this is going to be, the vector is going to be 24.8 meters per second, and comma 51 degrees above horizontal. Okay, so there's our initial. So if you just want the horizontal component of this guy, you simply have to multiply it by the cosine of the angle that it makes with respect to the horizontal, right? And so just, if you recall, there's our V0. And so this one here is going to be V0 times the cosine of theta. And this is going to be V0 times the sine of theta, right? Because, and these just follow from trigonometry, right? This is a right triangle, and so these just follow from that. So the V min is Vx, and so this is equal to V0 times the cosine of theta. And so this is going to be 24.8 meters per second times the cosine of 51 degrees.
So, Professor, just one question.
Yeah, go
We
ahead.
calculate the component with the initial velocity, right?
That's correct.
The initial.
Yeah, that's right. Yeah, so
Usually we use the initial, or it depends the question.
Yeah, so just in general, anytime you have a velocity that has more than one, that has both x and y components, if you just want the x component, you times by the cosine of the angle. If you want the y component, you times it by the sine of the angle. This is true for any velocity that you need to know the components of. So if we do this math here, okay, that's curious. Okay, so we do this math. Okay, hang on. I have to do this on my calculator because I can see that in my notes they put I have the wrong angles, so I gotta do this again. Okay, let me quickly do this. So um, we got degrees. So 24.8 times the cosine of 51 degrees. So that does work out. Okay, that is correct. All right, so I do have it right. So that's 15.6 meters per second. Okay, so that's part A.
Mhm.
And let's look at part B. So for part B, they ask, find the horizontal distance that the ball travels before reaching the goal. All right, so basically what we're talking about is we're talking about the distance between this location here and this location. Okay, so we're talking about this distance. This is what we're calling D. Okay, so that's part B. So in fact, I'm going to go ahead and start part B down here because I have a little bit of room. Um, so for part B, we have to find this distance that it traveled. So we've got delta x is equal to D, and that's what we need to find. Uh, the initial speed along x is simply what we found here, 15.6 meters per second. That's what we found in part A. And then the final speed along x is the same because the speed along x does not change. And then the acceleration along x, of course, would have to be 0. Okay, so this is what we know about the x motion. So let's take a look at the y motion. So delta y, it was given that, this high point where the ball begins to enter the goal is 2.75 meters above the ground. Okay, so this is going to be 2.75 meters. This was given. And then the initial speed along y is simply known as the initial speed times the sine of 51 degrees. And so then that, you do this, you put 24.8, you put sine of 51 instead of cosine. You do that, you should get 19.3 meters per second. Okay. And then let's see, then the acceleration along y is known as negative g, and that's minus 9.80 meters per second squared. Okay. And okay, so that's that. So in order to find the distance, basically what we need to do is we need to figure out the amount of time it takes for it to reach this point. Once we have the time, then we can work out the distance, because we know the horizontal component of the speed. So once you know the horizontal component of the speed, you know the time it takes, you can simply multiply those two together to tell you how much it traveled, starting from here and ending up over here. All right. And so to work out the time, we have to use the y, we have to consider the y motion. Because in this case, we've been given that it reaches a particular y position. And so we have to use the y motion to work out the time from. And then once we have the time, we'll go back to the x motion to work out this horizontal separation that we're being asked for. Okay, so for y, the y motion is accelerated, and so we can use this equation here that we have seen. Delta y is v initial y times the time minus 1/2 gt squared. Okay, so this is just like the one that has v initial t plus 1/2 at squared, but I went ahead and I plugged in minus g for the y acceleration, and so it looks like that. And so what we can do now is we'll go ahead, we'll put 2.75 meters, then we have to solve for the time. Okay, but we're going to be solving a quadratic. So we're going to use the quadratic formula, and we have to, because delta y is not 0, delta y is 2.75 meters, right? It's up there. So so let's do that. I'm going to go ahead and move over to the next page here. So we have here, I'll just repeat the equation I had. Delta y is equal to v 0yt minus 1/2 gt squared. And so we're going to use the quadratic formula. So let's write this in a sort of quadratic looking form. So we have minus 1/2 gt squared plus v 0yt. We're going to subtract delta y from both sides. So we get minus delta y is equal to 0. And so the quadratic formula says if you have ax squared plus bx plus c equal to 0, you solve this, you get x is equal to minus b plus or minus square root of b squared minus 4 times a times c divided by 2a. So we'll simply translate that over to here. And so we get t is equal to minus v0 y, okay, plus or minus the square root of v0y squared let's see, minus 4 times this guy. This becomes plus. Or no, actually it doesn't. Here, let me not have negativitis here. So this becomes minus, right? This is minus, then we have 4. And then our a is this guy, so this is going to be minus 1/2 g. And then c is this guy. This is going to be minus delta y. Okay, so that's 4ac. And then we're going to divide that by twice A. Okay, so that's what we have, and that's what we have. So we can plug in the numbers. So you plug this into your calculator. So what we're going to do is we're going to plug in, so this guy is going to be 19, this is going to be 19.3 meters per second. Okay, so that gets plugged in here and also over here. And then G, of course, this guy, we're going to plug in, we're going to plug in 9.8 meters per second squared. Okay, then this guy, we're going to plug in 2.75 meters. And then down here in the downstairs, we plug in, again, 9.80 meters per second squared. And so you do this in your calculator and you fumble with it for a while. Now, I did provide, I think, instructions on how to place this quadratic formula into your calculator so that you don't have to mess with this so bad. Let me see if it's still up there. Let me make sure it's still there. Oh, hang on. So I gotta, let's see. Right, so I think I put it in your shell. If not, I think I will. Let's see, here you go. How to use a quadratic formula. Yeah, so if you have a TI-84 Plus, you can program it into the calculator. And, you know, I invite you to do that. If you do have this type of calculator, I invite you to go ahead and watch this video if you don't know how, and put it into your calculator so that you don't have to fumble around whenever you have to solve a quadratic. You know, in this class, you're going to have to solve a few quadratics. Same thing if you take Physics 220, there's going to be some quadratics you'll have to solve. Okay, and so, you know, if you have this at your fingertips, then that is good, that is helpful. Okay, and so how did I get here? Whoops. Make sure everybody saw that. So what I did was I went to modules and I went into the Start Here module and I clicked on the how to use the quadratic formula, and then there's the short video and the little information guide that tells you how to do that. Okay, so let's go back to where we were. So we're going to go ahead and plug in our numbers into the thing here. So if you plug it in correctly, what I claim is that you're going to find that there's going to be two solutions for t. So t is either going to be 0.148 seconds, or it's going to be 3.785 seconds. And so which one is the one that you pick? What do you know, which of these two do you take and use? Well, you have to go back here and take a look at this here. So you notice that one of my solutions for time was a smaller number and one was a bigger number. So what exactly is going on? What this is saying is that there's actually 2 points in time when the ball is up at the height of 2.75 meters. It happens here, but you see it also happens over here. So it happens early on, and then it happens again later. And we're interested in the later time because that's the time that the ball is going into the goal. All right. So the earlier time that you see corresponds to this. The later time that we saw corresponds to this. Right. Both of these are points at which the ball is at 2.75 meters above the ground. Right. So this is 2.75 meters. So if we go over here, we're going to pick this guy. We're going to pick this as our time. And then we're going to go ahead and we're going to plug this in to delta x. So we have delta x is equal to v 0x times time. Right, the acceleration is 0. So this is all you have. And so, so we're going to plug in what we found for the x speed, which was 15.6 meters per second. And then we're going to times it by 3.785 seconds. And so you do this, you get 59.1 meters.
I have a quick question. Usually when I have two value for the time, I take the higher value for t, the time.
Not necessarily. In this case, yes, because we're being asked, you know, what happens later when the ball is going into the goal. But, you know, sometimes you may be asked what happens earlier, you know, or sometimes even you may be asked what happened in the past, right? If the time ever comes out negative, that means it's telling you about something that happened in the past, right?
Which is the smallest one?
No, in this case, you know, both times are in the future, right? But if you ever get a negative solution, that's time in the past. So yeah, so in this case, you know, the way we know to use the bigger number is simply because we know we're being asked what happens over here when the ball has gone all the way to the goal. And so that means we have to take the later time, not the earlier one. Okay, so that was part B. Any other questions about part B?
And for the time, you take 1 to 4 significant number, or does it matter?
So it doesn't matter that much. You know, when I'm grading the exam, I'm not going to be looking very closely at your significant figures. I'm mostly interested that you do the correct algebra and you've used the correct logic. But, you know, for something like this, if you have to use, you know, an intermediate result to get a final result, it's better to have, you know, 4 significant figures so that you have a more accurate final result. But I'm not going to be looking so closely at that on your exam. Okay, so let's look at part C. So for part C, it asks, what is the velocity, both magnitude and direction, of the soccer ball as it enters the goal? So if we go back to here, so by the time the ball is over here, now the velocity is pointing downwards and to the right. So now it's pointing like this. Right now the velocity is kind of in this direction, right? So this is V final. We'll just call this V, right? That's our final velocity. It's doing this as it goes down to the goal, right? I guess I didn't draw that so well, but you get the idea, right? It's not going up and to the right anymore. Now it's heading down and to the right. So the question is, how do we find it? So for part C, what we're going to do is we need to find Vx and we need to find Vy. And so that V is simply going to be, we use Pythagoras, like that. And so, so what do we do? So basically, so this guy is simply, we already found it. This guy we found is 15.6 meters per second. This one we don't quite know yet. We have to work that out. So how do we work this out? So we go back to our big five. So let's go back to our big five. And so that's over here. And so we're looking at the equation that tells you what is the final speed given the initial speed and given some acceleration and some amount of time. Okay, so the time we worked out, we did the quadratic, we found the time. We know the acceleration for y is going to be acceleration of gravity. We know the initial speed of y because we worked that out. We found 19.3. And so we can plug these in and find the final y by using this equation. So let's do that. So what we have is we have Vy is equal to V initial y plus AT, but that is equal to V initial y minus GT, because, oh, this should say AY, sorry, because AY is equal to minus G, right? Gravity. Gravity. So, so we can work out now Vy using this information. So we get 19.3 meters per second, and we're going to subtract 9.80 meters per second squared. Oh, and actually up here there's something else I forgot to write down. The time is 3.785 seconds. Okay, and then we're going to have 3.785 seconds. So inverse seconds squared cancels with seconds. So we just have meters per second, which is good. So you plug this in here, you actually end up with negative 17.8 meters per second. Okay, so this is now your final y component of the velocity. Okay, and so now we can plug this and this in here. So now the magnitude of the final speed, or I should say the final speed, is just the magnitude of our vector. So that's going to be 15.6 meters per second squared plus negative 17.8 meters per second, and we square it. So you do this math here, you get 23.7 meters per second. Okay, so that's the magnitude. And what about the direction? So for the direction, it's helpful if we draw a picture. So there's our V, and so it's going down and to the right. So this guy here, that's our Vy, and this here is our Vx. And so the question is, what is our angle? And so this is the angle we're looking for. And so you can simply take, we can simply take the inverse tangent of the y component divided by the x component. So the angle is going to be the inverse tangent of Vy over Vx. And so this is the inverse tangent of negative 17.8 meters per second divided by 15.6 meters per second. And so these units cancel, that's good. You don't want to have units inside of your argument that you pass to a trig function, right? If you've got units in there, then something strange is happening and you should double check your math. Okay, so so this is tan of this. You do this and you get negative 48.8 degrees. And so it's negative because the, you know, if this is our horizontal axis, right, there's our, you see, that's a negative angle. Whenever you go clockwise, it's negative. If you go counterclockwise, it's positive, right? That's our angle convention. So there's your angle. And that pretty much wraps up your practice exam. So looks like we've done about 99 minutes. Are there any questions?
Again, just to make sure, if it goes with the same work clock, it should be negative sign.
That's correct. If it's clockwise, it's negative for the angle. That is correct.
Professor, could I see the screen for the calculations for 4A again?
Absolutely.
Thank you.
That's this one.
Thank you.
All right. Okay, anything else before I end the meeting? Okay. So good luck to all of you on the exam.
Thank you.
And, you know, if you need more time, just send me an email and it will not be a problem. Okay?
Thank you. Have a great weekend.
Thanks. You too.
Thank you.
Thank you.
Thank you, Professor.
Thank you. Have a good one.
You too. Bye.
Bye now.